That roof is on fire. Oh, we gonna take it high.
For engineering physics, X1B, right? Gotta make sure you guys know the difference. So for today's lesson, we're getting into the first chapter, which is simple harmonic motion, right? Now we're gonna do a little bit of worked examples to like help understand. But basically, first we have to know what is simple harmonic motion, right? Simple harmonic motion is a special type of periodic motion where the restoring force is directly proportional to the displacement, right? And it acts in the direction opposite to that of displacement. So a classic example of SHM, which stands for simple harmonic motion, that you may know of, is a mass attached to a spring. So in this lesson, we'll explore how to solve common problems related to spring mass systems, because that's kind of the first thing we do. But first, let's look at spring mass systems. We have to understand first, right? So with a spring mass system, it would basically be oscillating, and that's why we call it a simple harmonic motion, right? A good example, let me just look for a good example is this animation. It would be going back and forth like this. In this case, we have a mass of 0.75 kilograms, an amplitude of zero point 0.2, and a spring constant of 300 newtons per meter, right? Excuse me. As you guys can see, it oscillates back and forth, just like that, right? Similarly, I think there's a better example we can use as well. Okay, this one is not the one. Yes. So let's mess around with the parameters so we can really understand, right? Let's say we have a spring constant of 100 newtons per meter, and then we start displacing it, right? So the restoring force would be negative 50 newtons. Don't mind the arrow is pointing the wrong way. It's supposed to be pointing backwards, but I made a mistake, right? But yeah, as long as you guys get the point. So it's gonna be displaced to the right, and the restoring force would be pointing to the left because it wants to go back to equilibrium. Does that make sense? So it would basically come back here due to the restoring force, and then let's say and then it would go this side, and then the restoring force would be acting to the right, pushing it back to equilibrium again, and then it would just repeat. So it would basically be, that's how an oscillation motion kind of looks like, right? So it would be going back and forth. Obviously, in this case, it's a frictionless kind of system, therefore we don't really lose energy, so it doesn't really stop oscillating. It's an ideal scenario, which won't really happen in real life, but it's basically the point of an a simple harmonic motion when it comes to a spring mass system, right? So the key formulas we need to know is period. So how long does it take for one full oscillation to occur? The period is given by 2 pi times square root m over k, right? And the frequency, which is the number of oscillations per second, is just 1 over the period. And then the angular frequency, which is related to frequency, is 2 pi times the frequency, which is equals to square root k over m. So you may notice something interesting, right? We see that the period is equals to 2 pi square root m over k. So what does that tell us? That it tells us that the period is actually basically 2 pi over omega. You guys see that? So basically it's the same as 2 pi times square root m over k. Does that make sense? But yeah, that's basically how it is. So if you want to get into like the full derivation stuff, there will be other videos on that that you can find, elsewhere. We won't really be doing the derivation here. We just need to know and understand the formulas. And then for the force in motion equation, things. We have first Hooke's law, right, which defines the restoring force of a spring. You guys are probably familiar with this one. So this is basically how we get the restoring force. It's F equals Kx, or you know, if you're considering it going to the right, then it would be F equals negative Kx, as it applies, and so on and so on. And then for the equation of motion, excuse me, the position x at time t, which basically describes position as a function of time, right? Would give us x of t is equals to a cosine times omega t plus phi, where a is the amplitude and phi is the phase angle, right? Very simple, very easy. Now, let's deal with some problems, right, in regards to this. I don't want to. Okay, let's look for some easy examples, but if we cannot find any other examples, we'll just deal with those ones that are below this point, right? But I want to avoid them because I want better examples. Let's see here. Okay, so if most of them seem to have the same question, but let's just do this question, right? So they tell us that a horizontal spring with a spring constant of 300 newtons per meter with a mass of 0.75 kilograms attached to it is undergoing simple harmonic motion. So we need to calculate the period, the frequency, and the angular frequency of this oscillator. So we're going to be sticking very close to our beautiful formulas over here, right? Let me just open board so we can just try this question ourselves. Right. So first they tell us that K is 300 newtons per meter and our mass is 0.75, if I'm not mistaken. Okay, 0.75 kilograms. And they ask us to find the period. So we know that the period is 2 pi square root. Is it m over k or k over m? I tend to forget. M over k, right? So we already have everything we need to find the period. We basically just say 2 pi square root 0.75 over 300, and we get our period. Let me just put that on my calculator and get the answer. Let's see, 2 pi square root 0.75 over 300, and we get 0.314 seconds. So it's basically the same as pi over 10 seconds, right? If you want to be all technical. But that's basically it for A. Very simple. You just plug into the formula. Let's move on to B. So for B, they ask us for the frequency. Now, what do we know? We know that the frequency is 1 over the period. So it's just going to be, let's just say 1 over the answer. And we get 3.183 hertz. Again, very simple, right? For C, we want the angular frequency, which is going to be omega equals 2 pi f. So we just say 2 pi times 3.183, right? And we get 20 radians per second. Very easy again, and I think that's basically it. Very simple, right? But now let's deal with a more, equation of motion oriented type of question, and forget all these other ones because it's kind of the same if you really understand the formulas. You just need to apply your knowledge. Let's move to an equation of motion problem, right? So they tell us that a 0.75 kilogram mass vibrates according to the equation x equals 0.65 cosine times 7.35 t. So let's just write that down. I have a horrible memory, so I don't know how I intend to remember that, but we'll just see. So 0.65 cosine 7.35 t, was it? Oh, my memory failed me. Okay, for once in my life, somehow it has not. So then they ask us to determine the amplitude first, right? So that's how basically the maximum displacement it goes to, right? Uh, and what do we know? We know that the standard for this formula is a cosine omega t plus phi. So what can we start to notice already? Phi is equals to 0, a mark that I hope you'll never get because, yeah, some of us have been through that, still depressed to this day, but moving on. uh, we get that this is basically out of the question, right? So now what does that tell us? That tells us that the amplitude A is equal to 0.65. Really easy, right? Like, come on, like, what? Like, crazy. Who would have thought, right? So easy to get that. And then for B, frequency, I hope it's the same. I hope it's easy to get. Who thought physics could be easy? It's really surprising sometimes. But to be fair, it does get a bit more difficult. But I believe in you guys. You guys inspire me. I feel like you guys can solve any problem I throw at you. Right? You guys are very, very good at physics. I can tell. But yeah, frequency. So then you guys might be wondering, how do we get frequency in this case? Or maybe you already figured it out, right? Because we have omega. So omega is 7.35 radians per second. Amplitude is meters over there. I assume it's meters, right? And this is 7.35 radians per second. So what do we know about omega, or angular frequency and frequency? We know that this is basically equals to 2 pi f. So f is going to be equals to omega over 2 pi, of which, if you notice, is basically the same as 1 over t, right? Because we said t is basically equal to 2 pi over omega. Do you guys still remember that? Or did I catch you slipping? Must wake up. There's no time to play here. It's physics. But yeah, now we basically get the frequency. Easy as pie, right? So we got 7.35 over 2 pi, and that's 1.169. So let's just write that down. 69 hertz, right? You could round it up to 1.17, whatever you prefer. But yeah, that's basically it for frequency. Again, very simple. For the period now, well, I just told you guys, the period is basically just like 2 pi over omega. Like, it's like easy, like, I don't even know, like, just gotta say 1 over um, frequency, of which you already have the frequency, right? So it's 1 over 1.169. And we get 0.854. So that means this thing oscillates in 0.854 seconds. You could round it up to 0.85 or 0.855, whatever you prefer, right? Because there's different rounding standards. But I just like to do the whole like three three units after the decimal pretty consistently. But moving on, now we need to get the spring constant, right? So how do we get the spring constant? Hmm. Do you guys remember that omega is basically um, square root is a k over m? Could also use the fact that t is equals to 2 pi square root m over k and just solve for k. Both ways work, just whatever you prefer. It's very nice here. Now, you even have choices. Like, since when? Since when is physics this nice? But yeah, let's see. It's square root k over m. So we'll just use omega to make things easier for ourselves, right? So we can just square both sides. Right. Mm. Don't mind my egregious parentheses or brackets, whatever you want to call them. So it's going to be k over m. And then k is basically going to be w squared times m, right? Now we have everything, or do we? We have, let me scroll down. We have the mass, so we can just go straight into it. We have omega, which is 7.35 squared times the mass, which is 0.75, right? I did write out the mass, so it is uh, 0.75. Well, that's the previous question, but I think they have the same mass. Okay, they do. So then now we just get our k, easy as that, right? Now, obviously, this is not something you would get in like a test, but just to introduce you guys to the topic, right? I'm very hands on, so I like to teach practically or tutor practically, right? This is basically how you can understand simple harmonic motion in terms of problems. There are more difficult problems, right, that I do with my students, but for this, it's just easy as that. So that's basically um, how I can introduce simple harmonic motion when it comes to spring mass systems. You might think it ends there, but it really doesn't, right? So if we move on, and just move to this. Okay, yeah, let's move to this, right? So there are other ways, there are other types of oscillators, and the next you may have already seen here is the simple pendulum, right? So a simple pendulum basically consists of a point mass um, or a bob. I hope you don't know anyone called Bob because now you have to think about them bobbing around. It's not nice. But yeah, it's a point mass or a bob, whatever you wanna call it. If you don't like someone named Bob, you're sorry, man. Like you're just gonna have to deal with Bob a lot, like in this topic. But yeah, so Bob is suspended from a string of length L, right? So he's hanging in the air. I don't know why. It's very weird for Bob to do that, but Bob is a silly guy. But for small angles of displacement, it approximates simple harmonic motion. So the restoring force is the tangential component of gravity, of which is F equals negative mg sine theta, right? And using the small angle approximation, which is that sine theta is approximately theta, we find that the acceleration is equals to negative g over L times S, which is the condition for simple harmonic motion. As you can see, it oscillates back and forth, right? It's just hanging around. Bob is doing his thing as per usual. He's just going side to side. Bob is a chill guy, right? So for the period of a simple pendulum, it's the same, right? It's 2 pi over omega. So our period is 2 pi over omega. And omega in this case is square root g over L. So basically, our period t is going to be 2 pi times the square root L over g, right? As it states here. Just highlight that like that, right? And here we have basically a sort of interactive pendulum that we can mess around with to see how length and gravity affect our guide bulb here, right? Let's say we decrease the length. What's going to happen to the period? It's going to decrease. Because think about it. Now it needs a lot less time to, go about its oscillation, right? Because the gravity stays the same. So that means the length is basically um, directly proportional to the period, right? Or you could say the square root of length is directly proportional to the period, and vice versa, right? So if you increase the length, it's gonna take more time to swing, to to finish one full oscillation, to finish one full swing, right? And we can see that presented by the period here. Now let's say we have 0.7 meters on Earth. The period would be 1.68 seconds. And then let's do that same thing but on the moon. We all love the moon, right? The guy we all see at night, shining in white, in an ethereal white, like a lady in a sundress, whatever you want to call it. I'm getting poetic, but let's move on. If I remember correctly, the gravity on the moon is 1.6. Why am I struggling to get 1.6? Just give me a second. But yes, notice how with the same length, but a lower gravity, the period has increased. It now swings much slower, as we can see, because the gravity has decreased. Just for reference, so that you guys can remember, right? This is 4.16 seconds for the moon. Excuse me. But we go back to 9.8, like we're used to, this dreaded 9.8. I kind of wish we lived on the moon, right? Just to float around for fun. But yeah, we get 1.68 seconds. That's basically almost 4 times less time for it to finish a full oscillation. So that's basically the basis of this simple pendulum, right? That means gravity is inversely proportional to period. And we can see that in the formula, right? Because it's square root L over J, right? But moving on, another way we can visualize simple harmonic motion is by comparing it to uniform circular motion, right? So we can visualize SHM as a one-dimensional projection of uniform circular motion, right? To help us understand its sinusoidal nature and the phase constant. So if you look at it here, right? Let's say this is the projected position. So at A, it's going to be at 1 times the amplitude. That means it's at the maximum, right? It's fully out to the right, we could say. And then as we move, we go to 90 degrees. Just scroll up a bit so you guys can see, right? It's at 52, but let's take it all the way up to 90 degrees and look at it. We get this. So it's now in the middle. What does that mean? It means it's at equilibrium, right? So our amplitude, and I mean our position is 0 times the amplitude. So it's basically just 0, which means it's at equilibrium. In reference to the equilibrium, it's at equilibrium. Makes sense, right? But if we move further to our favorite, other number, other angle, which is 180, as you can see, it's completely to the left. So we get -1 times the amplitude, right? Pretty straightforward. And now we go to 270. Again, I don't know who likes 270. I feel like it's ignored too much, but you know, I like 270 for some reason. But yeah, we get another point of equilibrium. And then if it makes a full rotation back to 360, we get, you know, 1 times the amplitude. So it's all the way to the right again. So if you can imagine it, it's basically going back and forth like the example I showed you guys earlier, where it's just springing back and forth. I'm looking for that same thing. This one is not the same, but because of this weird red F, but it's basically how you would see it, right? It's oscillating back and forth. Um, but before we continue with other stuff, let's just do a little bit of problems for a simple pendulum, because that circular motion problem is kind of like relating it to more of the spring mass system, right? But yeah, let's try some problems when it comes to this. So I think there should be some problem. Let me just do this. Okay, this is literally what we just learned, right? So they ask us what the period and frequency of a simple pendulum that is 70 centimeters long on the Earth and on the Moon. So our gravity on Earth is 9.8 meters per second squared, and our gravity on the Moon is 1.6 meters per second squared. So let's deal with this problem, right? So they want the period and frequency on different places. Let's just scroll down and start fresh, right? So they tell us that the length is 70 centimeters, which is 0.7 meters, right? If I remember correctly. Okay, 70 centimeters. And then we have G Earth, 9.8 meters per second squared. You know this, and OGM is 1.6 meters per second squared, right? So now we need to find the period. So let's start with Earth. The period on Earth would be what? 2 pi square root L over G, right? Now, if you have noticed something, it's that basically this doesn't depend on mass at all, right? So mass is not a factor in this case. You may have been wondering, like, oh, what about Bob? How heavy is Bob? You know, we all know Bob is a heavy guy, right? But in this case, Bob's weight doesn't really matter to us. Bob's mass doesn't really matter to us. We just need the length of the string attached to Bob and, you know, the gravity thereof. So you'll just say G. So we have 2 pi square root 0.7 over 9.8. So we get our period on Earth, right? And that's 1.679 seconds. And then the period on the Moon is gonna be GM similarly. So we just get 0.7 over 1.6, right? And we have 4.15. You could say 4.156 seconds. Easy as that. Now for the frequency, we know that it stays the same. Uh, it's basically just gonna be F over 1. F is equals to 1 over 2, right? So we can say Fe is equals to 1 over Te. So we say 1 over 1.679. And what do we get? 1.679. We get a frequency of 0.596 hertz. Same thing for the mole, right? Fm is just going to be 1 over Tm, and it's going to be equals to 1 over 4.156. And we get 4.156, 0.241 hertz, you could say. And it's as easy as that. Now, there are more difficult questions you could try when it comes to this, but just as an introduction to basically a simple pendulum kind of question, you would get something like that. Just more difficult, most likely, if it can be made more difficult. But moving on, right? Let's move on to the equation of motion. Okay, that we already did, but this could serve as a visual explanation. The graph is a bit janky, unfortunately, but it's something like this, right? It's it's very messy. I don't. We could model it and change the phase constant, but unfortunately, I didn't code it properly, so it doesn't necessarily work the way it's supposed to. So for now, just stick to what you understand, right? We could actually view um, these graphs, yeah. We could view it something like this, where this would be the amplitude, this would be the amplitude, the highest and the lowest points. Those are the amplitude, basically. Simple as that. And yeah, you could try problems like this that are more difficult. These are the ones I reserve for my students, right? But yeah, let's move on. So then there's the topic of energy in simple harmonic motion, right? So as this thing oscillates at different points, there's different. You could say there's different summations of energy. Not necessarily summations. The total energy, the mechanical energy stays the same, but it'll affect the amount of kinetic energy and potential energy at each point. Let me just open my notes here and start showing them, or rather transferring them to a screen so that you guys can see. But yeah, let's go back to open board here. Alright, our favorite, just so we can draw an actual picture of how it looks like. So if we have a spring mass system here, let's just say it like this. Guys, I'm a horrible drawer for the record, right? Art is not my thing. As much as I want to be good at art and drawing, it just evades me. It's one of those things. But yeah, let's say this is at its amplitude. So we'll just say x equals a, right? So that's our displacement there. And then here we would have x equals negative a. So that's the other point that would reach, as we've seen from the oscillation simulations, right? And then here we would get x equals 0. So it would be at equilibrium. Oh, excuse me. See what happens when you have a big breakfast, guys. Don't be like me. See, eating too much, it's a bad thing. But let's focus. We're here to chow course, not chow breakfast, but do chow breakfast, right? But yeah. So then we know that usually mechanical energy is just the summation of kinetic energy and potential energy, right? Well, then you may start to wonder what happens at these different points when it comes to kinetic energy and potential energy. Well, think about it like this. At this point, if you really think about it, right, this thing would be going back. Let's start with at maximum amplitude, right, to the right. If you think about it, it has just reached the end of its motion and it's about to go back. meaning it's basically yielding to the restoring force, right? So it wants to go back. So if you think about it, then the acceleration here will be max. So we have our E max here, but the velocity will be zero, right? Because it just came to a stop and it's about to go all the way back. The force is giving it an acceleration because we know about Newton's second law, which states that F equals ma, right? So our restoring force is giving this block an acceleration to the left. So that's where our Emax will be. Now, I'm sure you can probably guess what would happen in the middle. But before we do that, let's focus on this. It's basically the same, right? Now it's just that the restoring force would be going to the right, all right? And we have our maximum acceleration again. And our v is equal to 0 again, so 0 velocity. It's basically the same, right? Very simple. But then what happens in the middle? You might be wondering. Well, here, if you think about it, it would be going all the way and then would be reaching a point where it's basically at maximum velocity because it's been accelerating all the way from here until here, right? So the acceleration was creating a velocity, right? Was increasing the velocity because we all know that, you know, acceleration is basically changing velocity over time. So this velocity was increasing until it reaches a maximum at x equals 0 at equilibrium. Because once it passes this point, if you think about it, it's gonna start decelerating. So the velocity would no longer be at maximum. But then here, what also happens? The acceleration would be at 0 because now it stops accelerating. That's how it reaches the maximum velocity, right? And then now it starts dipping into the negative when you go to this side of the, you know, of the oscillator, you could say, whatever, of the motion rather. So that's basically how we can look at it. Now, what this implies is basically that here it's going to be PE max because the velocity is 0, meaning KE max would also be 0. KE would be 0, kinetic energy, right? And then here, our KE would be at max because PE would be equal to 0, right? Because there's no acceleration. And then same thing here would be PE max, right? Because KE equals 0 because there's no velocity. But here where there is velocity, the maximum velocity, we get the maximum kinetic energy. So what happens between these points? What happens here and here, for example? You might be wondering. Well, it's simple. At these points, you won't have a maximum potential energy and you won't have a kinetic energy maximum either. So it will basically go back to the default where it's just mechanical energy is equals to the sum of the kinetic energy and the potential energy. Simple as that, right? Very easy, very straightforward. Uh, and yeah, that's basically it for energy. If you look into it more, you could see that basically the mechanical energy is given by half k squared, and then we know the others to be half uh, mv squared, right? Plus half kx squared, if I'm not mistaken. Let me see. Yeah, it's half kx squared, right? So yeah, that's basically how you can see it, right? At this point, this x would be 0, hence why this is maximum. And at this point, v would be 0, so you basically get your mechanical energy being equals to the potential energy. Simple as that, right? But yeah, moving on. think that's almost the last of it. Uh, but that was basically just to explain this. And obviously, there's a conservation of energy. It remains constant. I forgot to state that, but yes. Now looking at damped oscillations, I mean, which we go into damping, right? You don't need to know this necessarily, but you just need to know about damped oscillations. You don't need to know the formulae, if I'm not mistaken. But yes, basically in real systems, non-conservative forces like friction cause the amplitude of oscillations to decrease exponentially over time. And this effect is called damping. So as I told you, we were looking at ideal cases where there would be no friction, but we know in real life there is friction, right? Just think about it. If there was no friction, if you've been ice skating, you know that there's a decreased like amount of friction, therefore you're more likely to slip. So that would basically be happening all the time. You'd be laughing all the time, seeing your friends, just trip everywhere. Like, oh my gosh, there is no gravity. I mean, there is no friction. I'm going to fall. Stuff like that. So obviously that has to be a thing. Unfortunately, I feel like it would be so much cooler in a world with no friction, but then we wouldn't be able to walk and drive anywhere. It's a double-edged sword. But let's just leave the world the way it is and focus on the damping coefficient, right? So in a real world system, we get something like this, where the amplitude is times by e to the negative bt over 2m. So b is what we want to focus on. It's the damping coefficient. And the term e to the negative, excuse me again, this breakfast, man. The term e to the negative bt over 2m represents the exponential decay of the amplitude, where b is the damping coefficient, right? As I stated. So we see that as we increase the damping coefficient, what happens? It decreases in terms of amplitude. So it doesn't go as far as it used to. This is the original. This is basically without a damping coefficient. It goes on forever. There's no friction. This is our ideal state. But as we go further and further, we see that it stops as time continues, right? And the amplitude decreases, meaning there's less and less total displacement over time. And by the end, by the highest damping coefficient, it only oscillates for a very short time, right? But here it oscillates forever, basically. But that's basically it for damping. Now, another thing we can look at is forced oscillations and resonance. So, when a periodic driving force is applied to an oscillator, it undergoes forced oscillation. And resonance occurs when this driving frequency matches the system's natural frequency, causing a dramatic increase in amplitude. So we have a periodic driving force, right, applied to an oscillator. So in this case, let's just mess around to see. So if we have a driving um, frequency of 3.8 radians per second, we see that it moves, right? Let me just do this so that it can stop moving and not be such a distraction. But we see that it basically moves a little bit, right? So this is basically a forced oscillation. We're forcing it to oscillate, you know. You don't force anyone to do anything, but physics is brutal, you know. It also forces us to think, unfortunately, you know. I know some students don't like thinking, but I'm getting carried away. let's see let's see what happens when the the frequency, the driving frequency reaches the system's natural frequency. So our natural frequency is 10 radians per second, and we're at 9.7 right now. And if you notice, it's already increasing in amplitude. So this is already starting to show effect, even though it's not at the the exact point of resonance, but let's just take it there to show what happens when it actually reaches it, and just look at the difference. I mean, I'm struggling again, but look at that dramatic increase in amplitude. That's a very high oscillation. It's a very high amplitude, rather, right? Because now the driving frequency is equals to the natural frequency of 10 radians per second. If we decrease it again, we see how there's a very dramatic decrease in amplitude. So I'm not quite sure whether we want resonance to occur or not, but I would think that we don't, right? Because that could stress the system out, getting such a dramatic increase in amplitude out of nowhere. Right. And then, even in these forced oscillations, you still have damping, so if we take it back to our driving force at 10, the same as our natural, and then increase the damping to the maximum, there's a very dramatic decrease in amplitude. It's not the same as before. But let's go cuckoo bananas for a bit. Let's go bonkers. What's physics without the crazy side? What happens if we take away all the damping and drive and put the driving I'm going to call it the driving frequency all the way until it reaches the the point of resonance, right? Well, first I want to see something. What happens if we increase the driving force? You see, even though we're past the point of resonance, the amplitude is not the same. You might have thought, oh, if we just increase the driving frequency, it'll just go faster, but it only goes basically as crazy as it can at the natural frequency. So let's just take away all the damp. And we get, this is just madness. This is just chaos, right? I doubt it would happen in real life. I hope it didn't because probably some people have to suffer for that. And eesh, yeah, we don't really like that, but this is what happens. It's the highest amount of oscillation you can get. It's even reaching here, right? So the force that it experiences, the restoring force it experiences, just think about how large it would be. But yeah, that was just to end off on a high note, right? That's basically our first topic, an introduction to our first topic. And thank you guys for joining me. And just to greet you guys, to rather say goodbye to you guys. Let's just go crazy again, right? Crazy again, crazy, crazier, right? But yeah, I hope you guys have a crazy good day wherever you're watching this, whenever you're watching this. Just enjoy physics for what it is and love the beauty of it, the craziness of it, the insanity, right? It can get very poetic at times, or maybe that's just me getting poetic myself. But yeah, thank you for